Mathematics has always been a language of patterns, logic, and problem solving. It has given us the tools to send rockets into space, build the internet, and understand the mysteries of the universe itself. But for all the progress humanity has made, there are still puzzles in mathematics so difficult that the brightest minds in history have struggled for decades, even centuries, without solving them. These are not your ordinary high school math problems. These are the hardest unsolved math problems in the world. Problems that continue to frustrate, fascinate, and challenge mathematicians to this very day. What makes these problems so mind-blowing is not just their complexity, but the fact that they are rooted in patterns and structures we encounter in everyday life. Prime numbers, shapes, equations, things that might seem simple at first glance, hide secrets so deep that no one has been able to fully unlock them. Let's start with one of the most famous, the Riemann Hypothesis. This problem dates back to 1859, when a German mathematician named Bernhard Riemann wrote a paper that has haunted the world ever since. At the heart of the Riemann hypothesis is the question of how prime numbers are distributed. Primes are numbers like 2, 3, 5, 7, 11, and so on, numbers that can only be divided by themselves in 1. They might sound simple, but they are the building blocks of all numbers. Every number you know can be broken down into prime numbers, just like matter can be broken down into atoms. Here's the strange thing. Prime numbers don't appear in any predictable order. Sometimes they're close together, like 11 and 13, and other times they're spread apart, like between 23 and 29. Mathematicians have always wondered, is there a hidden pattern behind their distribution? Riemann suggested there might be. He came up with something called the Riemann zeta function, a kind of mathematical formula that, if solved, would tell us exactly how prime numbers are spread out across infinity. The hypothesis says that all the so-called non-trivial zeros of this function lie on a straight line in the complex number system. If this turns out to be true, it would explain the distribution of primes in a way that would revolutionize mathematics. But here's the catch. No one has been able to prove it. For over 160 years, some of the smartest people in history have tried and failed. Why does this matter so much? Well, prime numbers are at the core of modern encryption, the way we protect credit cards, bank accounts, and secret information online. If we fully understood the pattern of primes, we might be able to crack or redesign cryptography in ways that could change cybersecurity forever. That's why proving the Riemann hypothesis isn't just an intellectual puzzle. It could literally reshape technology. Because of its importance, the Riemann hypothesis is one of the 7 Millennium Prize problems created by the Clay Mathematics Institute in the year 2000. These are 7 of the hardest math problems in the world, and anyone who solves one of them gets a $1 million prize. But even with that kind of reward, no one has cracked it yet. Another of these Millennium problems is the P versus NP problem. This one isn't just about math, it's about computers, problem solving, and even artificial intelligence. To understand it, think about puzzles. Imagine you're solving a Sudoku puzzle. It might take you hours to figure it out, but if someone shows you the completed puzzle, you can check in seconds whether it's correct. That's the difference between solving a problem and verifying a solution. In computer science, P represents problems that are easy for computers to solve quickly. NP represents problems that are hard to solve, but easy to verify when someone gives you the answer. The big question is, are P and NP actually the same? In other words, if it's easy to check the solution to a problem, should it also be easy to find the solution in the first place? If someone proved that P equals NP, it would mean that some of the hardest problems in science, medicine, logistics, and technology could suddenly be solved quickly by computers. That could mean rapid breakthroughs in drug discovery, optimized supply chains, even advancements in artificial intelligence that seem like science fiction. But it would also mean that encryption systems, which rely on certain problems being too hard to solve, could be broken in an instant. The world of cybersecurity could collapse overnight. On the other hand, if it turns out that P does not equal NP, then it means there really are problems that are just fundamentally hard, and no amount of computing power will ever solve them quickly. This would also be a huge revelation because it tells us the limits of what machines can ever do. So far, no one has been able to prove it one way or the other. Some mathematicians suspect P does not equal NP, but until it's proven, it remains one of the greatest mysteries in computer science and math. Now let's move on to another incredibly strange unsolved puzzle, the Collat's conjecture. This one sounds so simple, you'd think a middle schooler could solve it, but don't be fooled. It goes like this. Take any positive whole number. If the number is even, divide it by 2. If the number is odd, multiply it by 3 and add 1. Then take the result and do the same thing again. Keep repeating the process. For example, if you start with the number 6, you divide it by 2 and get 3. Since 3 is odd, you multiply it by 3 and add 1, which gives you 10. Then 10 is even, so divide by 2 and you get 5 is odd. So multiply by 3 and add 1, which gives 16. Keep going and eventually you'll end up with the sequence 4, then 2, then 1. Once you hit 1, the process loops forever. 1 becomes 4, 4 becomes 2, 2 becomes 1, and so on. The Collatz conjecture says that no matter what number you start with, you'll always eventually reach 1. Simple, right? Here's the kicker. No one has ever been able to prove it for every number. Mathematicians have tested it on billions of numbers, and it always works. But proving it works for all numbers, forever, is something no one has been able to do. The great Hungarian mathematician Paul Erdos once said, "Mathematics is not yet ready for such problems." That's how deceptively hard it is. What makes the Collatz conjecture so mysterious is that it seems to sit right at the edge of chaos. The numbers bounce around unpredictably before they settle down to the loop of 4, 2, 1. It's like order hidden inside randomness, and no one fully understands why. Then there's the Goldbach conjecture, one of the oldest unsolved problems in math. It dates back to 1742, when Christian Goldbach wrote a letter to the great mathematician Leonhard Euler. The conjecture is simple to state. Every even number greater than 2 can be expressed as the sum of two prime numbers. For example, 4 equals 2 plus 2, 6 equals 3 plus 3, 3, 8 equals 5 plus 3, and so on. It sounds straightforward, and indeed, mathematicians have checked this for numbers up to incredibly large limits, into the trillions. Every single even number tested so far follows the rule, but no one has ever been able to prove that it holds true for all even numbers, all the way to infinity. That's the tricky part about these problems. Just because something works for billions of cases doesn't mean it works for all cases. Without a rigorous proof, it's still an open question. These unsolved problems show us something humbling about mathematics. We often think of math as being complete, as if every rule and equation is already written down. But the truth is, math is full of mysteries, gaps, and questions waiting to be answered. Some of these questions have been around for centuries, challenging generation after generation. They remind us that for all our knowledge, there are still frontiers in human understanding. And the deeper you look, the more fascinating the connections become. Problems about prime numbers tie directly to the safety of your bank account. Problems about computation tie into the future of artificial intelligence. Problems that look like simple number games can hide the deepest truths about order and chaos in the universe. One of the other Millennium Prize problems that has puzzled mathematicians is the Navier-Stokes existence and smoothness problem. At first, this one might sound like it doesn't belong on a list of unsolved math puzzles because it's really about fluids, like water, air, and even the flow of blood. The Navier-Stokes equations are mathematical formulas that describe how fluids move. They were developed in the 1800s and are used everywhere today, in weather forecasting, in designing airplanes, in understanding ocean currents, even in simulating galaxies in space. So what's the mystery? Well, while we know the equations work incredibly well in practice, no one has ever been able to prove that solutions to the equations always exist and are always smooth. In simple terms, we don't know for sure whether the equations can describe fluid motion without breaking down into chaos or singularities, like infinite turbulence. If someone could solve this problem, it would give us a deeper understanding of the mathematics of fluids, something that could improve climate modeling, aerospace engineering, and many areas of physics. But despite decades of effort, the full proof remains out of reach. Another Millennium Prize problem is the Birch and Swinnerton-Dyer conjecture, which is all about objects called elliptic curves. An elliptic curve is a type of equation that looks simple on paper, but is deeply connected to number theory and cryptography. The conjecture says that you can figure out whether an elliptic curve has infinitely many solutions by looking at a certain function related to it. This might sound abstract, but elliptic curves are at the heart of modern encryption. Your online banking security depends on them. So if someone could prove or disprove this conjecture, it could lead to breakthroughs in number theory and possibly even new methods of encryption. There's also the Hodge conjecture, another of the Millennium problems, which deals with geometry at the most advanced levels. It asks whether certain kinds of geometric shapes, very high-dimensional ones that you can't even picture in your head, can always be represented by simpler algebraic building blocks. Solving this would help mathematicians understand the connection between geometry and algebra, two of the most fundamental branches of math. And then there's the Yang-Mills existence and mass gap problem. This one connects directly to physics. Yang-Mills theory is a mathematical framework that underlies our understanding of fundamental forces in the universe, like the strong nuclear force that holds atoms together. The problem is that we don't fully understand why particles described by this theory seem to have mass, a phenomenon known as the mass gap. Proving this mathematically would bridge an important gap between abstract math and the reality of the physical universe. Out of the 7 Millennium Prize problems, only one has been solved so far, the Poincaré conjecture. In 2003, a Russian mathematician named Grigory Perelman solved it, proving something fundamental about the shape of three-dimensional space. His work was so groundbreaking that he was awarded the Fields Medal, Aristotle, the most prestigious award in mathematics, but he turned it down, as well as the $1 million prize. His solution was a rare triumph in the world of unsolved problems, but the other 6 millennium problems remain open. Of course, not all unsolved problems are as formal or technical. Some are deceptively simple and could almost be explained to children. Take the twin prime conjecture. It asks a straightforward question. Are there infinitely many pairs of prime numbers that are only 2 numbers apart, like 3 and 5, 11 and 13, or 17 and 19? We know lots of twin primes exist, and mathematicians have found them even at unimaginably large numbers, but no one has ever been able to prove that the supply never runs out. It's like looking at the night sky and seeing countless stars but not knowing whether they go on forever. Another quirky mystery is the perfect cuboid problem. A cuboid is just a rectangular box, like a brick, with edges, face diagonals, and a space diagonal. The problem is to find a cuboid where all these lengths are whole numbers. We know of right triangles with all whole number sides, called Pythagorean triples, like 3, 4, and 5. We even know of three-dimensional shapes where some sides and diagonals are whole numbers. But no one has ever found a perfect cuboid where every single measurement works out to a whole number. It's not proven whether one exists or not. It's a puzzle that seems simple but hides incredible depth. Then there's the enigma of odd perfect numbers. A perfect number is a number that equals the sum of its proper divisors. For example, 6 is a perfect number because 1 plus 2 plus 3 equals 6. Another is 28 because 1 plus 2 plus 4 plus 7 plus 14 equals 28. These numbers fascinated ancient Greek mathematicians, and we know that even perfect numbers exist in abundance. But here's the question. Does an odd perfect number exist? No one has ever found one, and despite centuries of searching, mathematicians still don't know the answer. If one exists, it must be extremely large, bigger than anything we've been able to compute so far. Some problems connect directly to the real world in unexpected ways. For example, the mathematics of tiling, how shapes can cover a surface without gaps or overlaps, has led to discoveries about quasi-crystals, materials that were once thought impossible but are now used in real-world applications. Problems about sphere packing, which ask how you can pack spheres together most efficiently, connect to how data is transmitted across the internet with minimal error. Even the most abstract-seeming problems can have surprising consequences in science and technology. What makes unsolved problems so fascinating is that they represent the edge of human knowledge. They are the walls we keep bumping up against, the questions that no amount of computing power or clever tricks has been able to answer. And the truth is, some of these problems might remain unsolved forever, but that doesn't make them meaningless. In fact, the pursuit itself often leads to breakthroughs. Even failed attempts can open up new paths and reveal new connections. Think of the Riemann hypothesis again. Even though it hasn't been proven, work around it has led to entire new branches of mathematics. The journey to try to solve it has been just as important as the destination. The same goes for many other problems. They inspire new ideas, new tools, and new ways of thinking that ripple out into science, engineering, and technology. There's also something deeply human about these unsolved puzzles. They remind us that no matter how much we know, there's always more to discover. Math isn't a closed book. It's a living, evolving story. Every generation takes on the challenge, and maybe one day, someone will have the insight to finally break through. That person could be a professional mathematician with years of training, or it could be an outsider with a fresh perspective who sees something everyone else has missed. Until then, these mysteries remain open invitations. They sit there, daring us to try, reminding us that even in a world of supercomputers and advanced technology, there are questions that resist easy answers. And maybe that's the most mind-blowing part of all, that the universe still hides secrets in something as simple and fundamental as numbers. Thanks for watching, and don't forget to subscribe for more fascinating journeys into the mysteries of our world.